So today, the big picture is we're going to look at two particular shapes, ellipses and hyperbolas. Very, very different shapes, but a lot of similarities in how we derive the formulas. And the formulas themselves actually look really, really similar. So let's start with the ellipse. That's the easier one for most people to grasp. Okay, so what is an ellipse? Well, let's start with the same way we did circle and parabola last day. It's the set of points on a plane where the sum of the distances to two fixed points is constant. That's kind of a strange definition. Now, the way I was exposed to an ellipse when I was in high school, I still think is absolutely the best and really the only way anybody should ever be introduced to an ellipse. Some of you may have done this. I was going to try to do this in class and I realized I can't do it on this board. It won't work. So what we did in my high school class is they took a long piece of string, just a little piece of string, and then sort of taped it or stapled it or thumbtacked it to the board. Anybody know what I'm talking about here? How many did something of this nature, did the string? This is the way it should have been taught for every human being. Now, these are the two fixed points, and the length of the string is my constant distance. So what we did was, you took your pen and then you straightened this out. You put a little tension, but don't pull too hard because you don't want to uncork it. So as I'm moving around, what's going to happen is, right, the string will dictate how far I can go. Okay? So it's going to end up being, kind of this ovalish shape. Well, that's a terrible picture, I know. But when I stretch this out, it's going to come out, right? It's going to obviously go past the end of here because the string is longer than this distance. If the string were only from here to here, then you'd have a line segment. You agree? That would be boring. Now, the longer the string is, right, the more expansion. But the definition of the ellipse, so this point right here is the sum of these two distances, but the sum of these two distances is exactly the length of the string. Everybody see that? So that, to me, is the easiest way to demonstrate it, and then we just, can kind of carve it out. So let's talk about the properties. Let's talk about how to construct an equation of this, but that's pretty much what it is. Is there a center? Sure. The center would just be the midpoint of these 2 points. So that's the easiest part. That's not the critical thing. It's these 2 points. So what are these guys? Well, each one is a focus. The parabola has one focus. The circle has one focus. The ellipse and the hyperbola have 2. So what are these guys called? They're called, I always have fun with this one because most people mispronounce this, which I think is kind of funny. I've even heard math teachers mispronounce it. I learned, by the way, I've always known the pronunciation, but I learned there's actually a rule. It's called the law of C's. And I learned this when my children were in kindergarten and they were learning to read. There's actually a law of every word in the English language. Proper nouns are not considered words. So, Max, if you wanted to change, you can pronounce your last name any way you want, right? Because it's a proper noun, not a word. Every word in the English language actually follows the same rule. I didn't know this until my kids were learning to read. And by the way, this makes it easy because nothing sounds worse than when you take a word like math or science and you mispronounce it. It kind of makes you not look that smart, right? It's like we're mispronouncing calculus, Cat, century, city, country, cut. In other words, K, S, S, K, K. Every word in the English language, when C is followed by a vowel, either makes the K sound or the S sound. And there is no exception. And if there is, it's because they're mispronouncing it. So therefore, how do we say this? Foci. There is no such word as foci. And by the way, if there was, it'd have to be spelled F-O-K-I. Now, I have fun with that because I have people all day, I want to talk about the foci. What's the plural of matrix? Is it matrices? no, it's matrices, yeah. Index, indices, vertex, vertices. You already know this. You already have so many words. You go, oh yeah, I automatically change it to an S sound because it's CI. Okay, so I'd like you to pronounce it correctly because otherwise it does sound kind of silly, right? we talk about the vertex. I've actually already had people ask me about the vortex of the problem. No, vortex is something different, but it's probably not the problem. So how do we come up with an equation based on this? Well, let's start the easiest way. Let's start with an ellipse that is centered at the origin, okay? Let's say I have an ellipse. Now, by the way, your ellipse is either going to open horizontally or it's going to open vertically. That doesn't change anything in terms of how you do the problem, but it does in terms of the identification. If it opens horizontally, then that means my foci are sideways. If it opens vertically, then my foci are going this way. Because think of the string. You know, I would have had to go this way if it were opening vertically. Not a big deal. So let's suppose that my center is at the origin. I'll do my best to draw something semi-accurately here. Okay. Now let's say that our foci are maybe here and here. That's not too far. Let's call the coordinates of the foci c comma 0 and negative c comma 0. Let's call this point here a comma 0. Let's call this point here negative a comma 0. Let's call this point here, how about 0 comma b and 0 comma negative b. So clearly we want to establish a relationship between the a, the b, and the c. So these two guys are the foci. Technically, these 2 points right here are referred to as vertices. What's strange about an ellipse though, we don't call these guys vertices. I would be inclined to call all 4 of them vertices because those are the 4 points you kind of need in order to, if you're going to draw this thing, you kind of need all 4 of those, don't you? But for some reason, in the strictest sense, only these guys are referred to as the vertices. I don't know. I have no problem if you said the 4, right? Because we all know what we're talking about here. So if I took any point on the ellipse, let's say that one right there. Okay? Let's call that, how about D1, and let's call that one D2. I have 2 different distances. Those 2 distances have to add to a constant. Right? Remember, like I started, the length of the string, if you will. That's what those 2 distances are. But do I have any idea what the length of the string is? Actually, we do. Because if I said, well, how about from here? Well, what is the distance from here to this focus? What is that distance? So in other words, D1 plus D2, whatever they add up to as I move around, it's got to be constant. But if I just start with that point right there, how far is it from here to here?
A plus C.
A plus C, exactly. And how far is it from here to here?
A minus C.
A minus C. Oh, we know the constant, don't we? The length of the string is actually the distance from here to here. That's how long the string is. Oh, that made it easy, didn't it? So that constant distance, when I said the sum of these 2 focal distances must be a constant, turns out it's exactly 2a, and where that's the a. Cool. Okay. So I need to come up with an equation where I have D1 and D2 and then add them up, set them equal to 2a. A would be known, by the way. A is not unknown. A is a constant. Right? So what is D1? Let's write it down. D1 would be, think distance formula. So x minus x coordinate squared plus y minus y coordinate squared under square root. So what would that be? X minus this x coordinate would be this value minus this value would be
X minus C, X plus C.
Wow, that was painful. Okay, x plus c. Y minus this value would be
Y.
just y. Everybody's waiting for somebody else to answer the question that isn't really that hard of a question. Okay, what's D2? Well, same thing. So now I'm going from here to here. So x minus
C.
c, that's different. And then y minus
Y.
0 once again. Oh. Okay. So this square root plus this square root equals 2a. Agreed? All right. So that'll be an easy thing to solve, right? Or, wait a minute. Ooh, back in remedial algebra, you did problems of this nature. I'll give you an example. I'm not worried about the answer, but you did things like, okay, I need you to solve, 2x minus 1 plus 3x plus 4 equals, let's make up a 6. Well, just square both sides. Well, that would be a terrible idea.
No.
You made it more you square both sides, or now you're gonna make it more complicated. No, I don't want to square both sides. I want to take one of my square roots, throw it to the other side, then square both sides. If I square both sides, it's not getting easier, it's getting more complicated. They still have square roots with now bigger terms. Okay, so go back to here. If D1 plus D2 equals 2a, then the easiest way to attack this would be to say D1 equals 2a minus D2, and now square both sides. I'm still going to have a square root, but everything else is going to clean up really, really nicely. Everybody see what I'm doing here? This is algebra. This is not calculus. This is an algebra thing that everybody's done before. So D1 squared would be 4a squared minus 4a D2 plus D2 squared. I'm squaring both sides. So I'm going to save myself some time and just go directly to that. So when I square D1, I have no more square root. Okay? Maybe she got black here. And I would have x plus c quantity squared plus y squared equals 4a squared minus 4a times that icky square root plus the square of that thing. All right. Are we going to get some canceling going on here, you think? Yeah. But before I do, why don't we go ahead and square these two terms? That's going to be x squared plus 2cx plus c squared. This is going to be x squared minus 2cx plus c squared. Now the canceling is real obvious, right? I have an x squared that cancels. I have a c squared that cancels. I have a y squared that cancels. So far, so good? Now, I still have one square root left, but I have one square root left. So maybe, let's take the square root and let's throw it on that side so we give a positive coefficient. And let's take this guy, the only thing left, and throw it to that side. Will that work? So let's rewrite what we have. Then I'll have positive 4a times the icky root equals, I'm throwing this to the other side, so it's going to be a minus now, isn't it? So it'll be 4a squared minus 4cx. Is there an obvious thing to do here?
Get rid of all the fours.
Yeah, get rid of all the fours. Do you agree with that one? Multiply through by a fourth, in other words. Let's get rid of the fours. Okay. So now I have a times that square root equals a squared minus cx. Okay? Now let's square both sides again. And when I do that, what am I left with? On the left side, I will have a squared times x minus c squared plus y squared. We'll multiply that out in a moment. On the right side, remember, right now I just have a squared minus cx. That's all I have. So when I square that, it's going to be a to the fourth minus 2a squared cx plus c squared x squared. So let's do this guy. That's going to be x squared minus 2cx plus c squared inside there. Okay? So now when I multiply through by that a squared, I'm going to have a squared x squared minus 2a squared cx plus a squared c squared equals a to the fourth minus 2a squared cx plus c squared x squared. Does anything combine or cancel? Do I have anything that's the same on both sides? That guy's
Isn't
going
this
right?
the plus y?
Say again?
We lost the y, didn't we?
Did I lose? Oh, thank you, Chase. Thank you. There should be plus y's. Plus. I don't want to try to squeeze it in. Let me just rewrite that. Yeah, that y squared's probably important, huh? There we go. Okay. All right. So what cancels then? Well, definitely this guy. I have an idea. Let's put all the variables on the left, and let's put all the scalars on the right. Might be easier to gather terms if I do that. So that means I'm going to take this term here and send it that way, and I'll take this term here and send it that way. Agreed? Okay. So now what will we have? We will have a squared x squared minus c squared x squared, so a squared minus c squared x squared, plus a squared y squared equals a to the fourth minus a squared c squared.
You put a squared y squared as a subscript 2.
Oh, thank you, C. Yeah, okay. Could I rewrite this as a squared times a squared minus c squared?
Yeah.
Huh. But this is all we have left now. We have a coefficient in front of the x squared, we have a coefficient in front of the y squared, and we have it all equaling a constant. Now, is a squared minus c squared positive or negative? Well, what's bigger, a or c? A. So a squared minus c squared is definitely positive. Do you agree? So let's multiply through by 1 over. Now I'm going to write this way. Let's see. Oh, actually, no, that's not what I want to do. I want to multiply through by the reciprocal of this guy, because I want a 1 on the right side. That'll kind of feel familiar to many of you. I'm going to multiply through by the reciprocal of this, which means over here, what will I be left with? I'll have an x squared over an a squared. I'll have a y squared over an a squared minus c squared, and that whole thing will equal 1. Remember, a and c I know. So now let's go back to our picture for a moment. Because I have this mystery third value b. You know, I just, for convenience sake, I said let's call it b, but we have no idea of the value of b, right? We could never possibly figure out the value of b, could we? These guys. What do those two green bars have to add up to? Don't they have to add up to 2a? So doesn't that mean that each of them have to be a? Huh. I called that C. I called that B. Is there a little Pythagorean thing going on right here?
Mm-hmm.
By the way, my hypotenuse would be the A. Huh. So what's the relationship between A, B, and C? Clearly. Wouldn't it be A squared equals B squared plus C squared in that picture? So therefore, what does B squared equal? Okay, check it out, folks. Does that kind of look familiar to you? That is the equation of the ellipse centered at the origin, where I went left and right A and I went up and down B. Now here's the beautiful thing about that equation. It doesn't matter if I'm opening vertically. A is the horizontal stretch, B is the vertical stretch. And you're always going to get the same thing. We said centered at the origin, though. Is it always going to be centered at the origin?
No.
No. Okay, so now we'll do our tweakage. That's the easiest part of the problem. To me, this is beautiful. This is just really beautiful. We're combining algebra and geometry here. We just come up with the equation of an ellipse, and that's the one you probably remember going all the way back to, ninth grade, saying, yeah, I know this equation. I don't know why. I just know that was true. But now you see where everything came from. And it came from the fact that we defined it in terms of the distance to the foci. So what if now, I got my, kind of this shape, okay. I still want the left and right to be A units left and right and B units up and down. I want that same. I want the exact same ellipse. I just want to move it. So what do? We replace x with what? X minus h. We replace y with y minus k, and we leave those constants. Now this is one of the rare times. Normally you wouldn't divide by a number, you'd just write that as a fractional coefficient. But most of us realize if I write it in this form, it's easier to read the information. So this is one of the rare times we actually choose. If you were doing a problem and the answer to the question was x over 2, you'd write 1/2 x. Because technically x over 2 is actually not simplified. You cannot write a result where your denominator is a number. You actually have to pull it out as a coefficient. It's not considered simplified. Think of the calculus. You don't want to do the derivative of the quotient because now you'd have to use quotient rule. You want to use a fractional coefficient because now it's easy. But we like to write it this way because for identification purposes, it's just much, much easier. Now, depending on which is bigger, it's going to determine the direction of opening. So here's the simplest way to think about an ellipse. If I'm given the equation in that form, which often you are, start from the center, and from the center go left and right A units, go up and down B units, and just kind of fill it in magically on your own. You're never going to be drawing ellipses, you know that. But you need to know what one looks like. Why? Because next semester you're going to do three-dimensional versions of these things. Oh, I need to know what they look like. I can't do a three-dimensional version. What do you suppose a three-dimensional version looks like?
Egg.
An egg. Good. Looks like an egg. That's called an ellipsoid. We love those names. Oid means, quite literally, oid means like. It's ellipse-like. Okay? So it's interesting. I laugh at this one. I remember very little about high school. I know I went to one. I do know that. I know I also didn't go quite often. Well, I grew up in Santa Cruz area, and I only ditched if it was a nice day. Because didn't go to the beach and stuff. And I didn't actually go to a very good public high school. I mean, it was so bad. I won't tell you the name of the high school. But you guys know what accreditation is, right? Every school gets accredited every 6 years. They go through. Mesa's always doing this, to make sure everything's online. Mine was the only school in the history of the Santa Cruz County to lose its accreditation. They fired every single teacher and administrator and replaced them and then fired them again, all in a 4-year period. The second round was to fix it up. So we had kids in my high school lose their college acceptances because they came from a non-accredited high school. Yeah, that's how bad my high school was. It was really that bad. In terms of academically, it was garbage. Okay, I somehow survived, mostly because I didn't go a whole lot. But I remember on the very first day of 9th grade, the basketball coach who was teaching, it was like, I can't remember if it was a history or geography, it was one of those kind of classes, where they have the basketball coach teach it. So there's not a whole lot of education probably going on. But on the very first day, he says, you're not going to remember anything you ever learned in high school when you're older. But you will remember this. The Earth is an elliptic spheroid. I've never forgotten that. And literally that is the lone thing I remember. And also because that actually isn't a thing. An elliptic spheroid. No, it's technically an ellipsoid, but I love it. It's sphere-like. But is the Earth a perfect sphere?
No.
How do you know that? You know that, but why?
NASA says so.
Centrifugal force.
we know it's wider. The equator, that circle is bigger than the longitudinal ones, right? We know it's very small, but
It's pretty close.
it's very close. That's why we say spheroid. But that was the one thing I remember from high school. I actually remember the coach's name. I don't remember a whole lot of other things. Okay, so let's start with a really easy one. All right, I've got x minus 3 squared over 16 plus y plus 2 squared over 36 equals 1. I want to find the foci. I could draw this thing free-handed in about 15, 20 seconds. Right? Everybody could do that. Just draw an XY plane, count, connect the dots. It probably won't look very good, but you got the point. But I actually want to know, where are the foci? Where are they located, the exact ordered pairs? So, you never have to draw the shape, which is every reason why you probably want to draw the shape. Because, like with the parabolas the other day, my center is about here, right? And I'll write that down. The center is where?
-3, 2.
Careful.
3, -2.
3, -2. Okay, there. Now, I'm going to go left and right how many units? By the way, this is important. We did this when we did methods of integration. When you're looking at this, do you see a 16 and a 36? No. What do you see?
4 squared.
You see 4 squared and you see 6 squared. Otherwise, you might move 16 units. But you see a 4 squared, you see a 6 squared. So I'm going to move left and right how many units from here? 4 units, about here and about here. I'm going to move up and down how many units? 6. So about here and about here. So now when I connect the dots, it's not going to be beautiful, but looks like this-ish. Okay? Are the foci located vertically or horizontally? Vertically, because it opens the long way. So the foci would be up and down from the center. So how do I find them? Well, remember there was a Pythagorean relationship here. It's real simple. What we generally do with the ellipse is we refer to the value of c as the focal length. With the parabola, what did we use? Last day. What letter of the alphabet did we use to refer to the focal length? Remember? P. Yeah, these are very different things. We use the letter C to refer to the focal length in this situation. We also use the C in the hyperbola just to make it easier to remember. So C is the focal length, but I can't tell you C yet, but I can tell you C squared. What's C squared going to be? It's going to be the difference of those two guys. Now, don't say 4 squared minus 6 squared, because that would make C imaginary. So bigger minus smaller, and what would this be? Number. 20.
Root 20.
No,
Equal to C.
it would be 20. So therefore, C would be
Root 20.
root 20. I can reduce that. I'll write 2 root 5. Great. So my foci are maybe here and here-ish. Can you tell me the coordinates? There's a little more space there. Well, do I know the x-coordinate?
3.
We all agree that the x-coordinate is 3?
Yeah.
For sure.
Now the y-coordinate, what?
-2 plus 2 root 5 and -2 minus 2 root 5.
That's it. -2 minus 2 root 5.
You don't need to express that as like a fraction or anything?
Well, it's the square root though, so I can't really. Yeah, by the way, on those rare occasions that C comes out rational, and it would be rare, on the rare occasions where C comes out rational, then obviously you can combine the values. But you have a rational plus an irrational, so you kind of have to leave it like that. There's really not a whole lot you can do there. But was this hard? No. Tell me the only mistake someone might make on this problem. apply it to the x-coordinate.
Uh,
Which would be true if,
it was sideways?
no, if those two numbers were, yeah, if those two numbers were reversed, that would be true. So the bigger one just tells you the direction of opening, that's it. That's it, don't put more into it than that. Now, one of my pet peeves with math books, when you were babies in algebra, they probably did everything right. Then the calculus books come along and what they do is they give you two versions of every equation. In Calc 3, it's worse. They'll give you 3 versions of every equation. You don't need 3 versions, all that does is confuse. And it's almost like the author doesn't understand the big picture. No, you only need 1 version of the equation. You just have to be smart enough to say, hey, I have to subtract in such a way that it stays positive. Most calculus books will tell you, no, a squared is the number under the x squared, period. That's what you learned your whole life. B squared is the number under the y squared, period. Same thing with hyperbola. But then the calculus books will say, well, it depends which one's bigger. So let a squared follow the variable that's, no. Because that means you're going to get the wrong answer exactly 50% of the time, because you're trying to learn 2 different formulas for the exact same shape. And then you're choosing which formula to use. Don't do that. That's just bad mathematics. No, it's too easy to get this right. So, does this problem ever become difficult? Well, it can. Hold on a second, let's see. One sec. So I've got x squared plus 4y squared plus 4x minus 32y hold on a second, let me make sure I have the right numbers here. Plus 52 equals 0. I think I got that right. No, sorry, plus, let me make sure I got this right. Hold on. That something doesn't feel right yet. Hold on. So that would be. Okay, yeah, I think I got this right. Okay. I would like you to tell me, well, basically where everything is. This is what we call the general form of a conic. Okay, I'll go back. This is something that you may or may not have seen before, but it's not that critical if you haven't seen it before. We call the general form of a conic anything that looks like this. Now, how do I know if this is an ellipse, let's say, versus a parabola? Well, in a parabola, b would be 0. In an ellipse, a and b would be the same sign. Because I could trick you and make them both negative, by the way. They have to be the same sign. As we're going to see later in the hyperbola, they're different signs. Well, what if a and b are the same number, period? It's still an ellipse, but what would it also be? What if these were the same number? I'm going to write it a different way. I have x minus h squared. I have y minus k squared. And I'm going to make them the same number. I'll just call it r squared for lack of a better name. What is that? A circle of radius r. So is a circle an ellipse? Yeah. Yes, it is. But what would that make the value of c then? Doesn't c squared have to be the difference of those two numbers? Yeah. So what would c be? 0. So if I take an ellipse, I have two foci. The closer I get, the more circular it would become. And if it turns out they're concurrent at the same point, then I really only have one, and we call that the center of the circle. Oh, so a circle is a special case of an ellipse. But everything that is true about an ellipse is passed on to a circle. Not true in reverse, but everything true about an ellipse is true about a circle. Oh, so that's why we don't do circles separately in this class, because a circle is just a special case of an ellipse. It's an ellipse that has a focal length of 0. So the two foci literally are in the same point, the center. So that would be the exception, obviously, not the rule. So I need to make this one look like this one. How am I going to do that? Take some derivatives, maybe?
No.
Integrate?
Isn't that like,
Complete the square, good. By the way, you learn complete the square in algebra not actually as the means to solve quadratic equations, because the quadratic formula is good enough. You use it really with conics more than anything else. Because I can't tell you anything about this in its current form. So what we're going to do is, have I done anything yet? No, I just moved things around. Now we know we can't complete the square unless the lead coefficient is a 1. So let's factor the 4 out of that and write this like that, shall we? Okay. Whatever I add to the left, I'm going to add to the right. The other day when we did a complete the square, we left everything on the same side because for that problem it was convenient. But now I'm just going to do on both sides. Okay, so x plus, what goes here? 2. What goes here? 2 squared. Okay? This is going to be 4 times y minus what squared?
negative 4 squared.
4, and then what goes here? 4 squared. Aha. Oh, but wait a minute. What did I actually add? I actually added 64, didn't I?
Yeah.
Does everybody see that? I didn't add 16, I added 4 times 16. So if I multiply this thing all the way out, I should get that thing exactly. So what did I add to the right side?
68.
4 and 64. I'm reminding you of something you learned as baby algebra students, but probably not a technique you've done a lot of recently. You're going to do a lot of it right here. So what have I got right now? I've got x plus 2 quantity squared plus 4 times y minus 4 quantity squared equals 16. But to make my life easier, what would I rather have on the right side?
1.
I'd rather have a 1. So then I'm going to have x plus 2 quantity squared over 16 plus y minus 4 quantity squared over 4 equal to 1. Is this now a more useful form of the exact same thing? What I told you and this are the exact same shape, but now I can read information on here. Okay, so let's start with the center. I kind of like to know where it is. Negative 2, 4, and the foci, is this going to open horizontally or vertically? It's going to open horizontally, so I'm going to keep the same y coordinate. In fact, let's go a step further. 2 plus, 2 minus. What's my c squared going to equal? Right, 16 minus 4 or 12. So c would be root 12, which can reduce. I'll put 2 root 3. So I'm going to move left and right exactly this many units. C is a positive number. C is not plus or minus. C is positive. I'm going to move left and right from there. 2 root 3, 2 root 3. So I've now given you the center. I've given you the foci. It'd be a fairly simple thing to analyze in the graph and so on. So far, so good? This is the worst problem. The one where you have to complete the square in order to give the information. It's much easier if I told you the center and the foci and all, a bunch of information, and you could construct the equation. That's actually easier. Much like the parabola we did yesterday, right, or last day. Depending on which information you're given. All my erasers are falling apart here. Now, there's another piece of this that will help us. All circles have the same shape. Agreed? Think about it. All circles have the same shape. All squares have the same shape.
Yeah.
Do all rectangles have the same shape? No, they can be skinny, they can be closer to a square. In fact, a square is a rectangle. Do all ellipses have the same shape? No, because they could be skinny, they could be almost round, things like that. There's actually a number, a numerical value that describes the shape, strangely enough. If I told you I'm thinking of a rectangle, it's 5 by 10, in your mind you see exactly what that is, right? Doesn't matter if it's horizontal or vertical, you know exactly what that is. It's 5 by 10. If I said it's 5 by 5, oh, it's a square. It's easy to picture that rectangle because it's only got 4 sides, and But if I said I'm thinking of an ellipse, and it's very round or it's very skinny, that's kind of relative. It's like, what do I think is round might not be what you think is round. So there's a number, it's called eccentricity. And this was a terrible idea, but guess what variable they use for eccentricity? E.
Oh, no.
What's the single most important number in all of math and science? E. Yeah, you really shouldn't be using E as a variable, but I will promise you this, you're never going to use the number E when you're doing an ellipse. Okay, just to be safe, there won't be any E's showing up, there won't be any logarithms showing up. Okay, so this will be safe. I think it was a terrible idea. Heck, at least use a capital E. Nope, we always use a small e, which has meaning, but in this context it means eccentricity. Eccentricity is defined to be the C over, now this is, I hate this definition. Does anybody know what we call this length, this numerical value? This is terrible, terrible.
Is it diameter?
It's called the major axis. The number, not the line segment. Now, you think of an axis as a line. That distance, the 2a in other words, right? Or in this case, it would be 2b. That distance is called the major axis. Well, then what do you think we call this? We don't have a name for it. There actually no such thing. By the way, I would call it minor. There actually is no such thing called a minor axis, then why are we calling it a major axis? But the worst part is the major axis is a number. It's not actually the line segment. I find that to be not useful information, okay? But that is the number I need. Now remember, the length of the string, if you will, is the length, the major axis. That's the key number. But from the center, I'm not moving twice, I'm only moving that many. So it's C over half the major axis. This is the definition of what eccentricity is. It's the focal length divided by. So think of it this way. If this is the focal length and this is half the major axis, it's simply this quotient, which means that eccentricity must always be less than what? 1. Because the focus can't be on the outside of the ellipse. That's impossible. But as this gets more and more and more and more circular, in fact, in a circle, the focal length is what? 0. So technically, the equal 0 would only occur in the case of the circle, by the way, but it is possible. So there's a really easy way. And again, I was shown this many years ago, even before Professor Newton. I had high school mathematics from people who probably weren't math teachers by trade, probably the basketball coach kind of person. All right. Here's my ellipse. Here's my ellipse. That one is circular or really close to circular. This one's really, really long and skinny. Well, if this is really long and skinny, wouldn't the focus be really, really close to the edge?
Yeah.
The longer and skinnier it is, the closer to the edge. So the more round it is, the closer eccentricity is, closer it is to 0. And the longer and skinnier it is, the closer the eccentricity, it's never going to equal 1, but the closer it is to 1. Anybody have a really easy way to remember what an eccentricity is? When it's round, it's close to 0. When it's
Not.
Doesn't that kind of look like the number 1? This is the way I learned it. It's like, if it looks like a circle, it's close to 0. If it looks like the number 1, it's close to 1. It's actually that easy. So the longer and skinnier it is, whether it's horizontal or, I draw it vertical because now you say, oh yeah, I can see the 1 right there. So if I had something that was really, really long and skinny, the eccentricity could be, 0.99. 0.9 is really close to 1. If it was almost a perfect circle, the eccentricity might be 0.1 or 0.01, really close to 0. The rounder it is, the closer it is to 0. If it is perfectly round circle, then it is 0. Oh, so let's go back to this one here. What is the eccentricity of this? Because that's going to be one of the things. So there's really only 3 things that are relevant here. If I gave you the equation and nothing else, you tell me where the center is, you tell me where the foci are, and the eccentricity is a numerical value that literally tells me exactly what the shape is. All ellipses with a given eccentricity are the exact same shape. The size can vary. If I told you I'm thinking of a circle, do you know how big my circle is? No, you'd need to know the radius. But you know what it looks like. You know the shape of my circle. If I told you the eccentricity, if I said the eccentricity is, 0.5, it could be any size you want, but they would all look exactly the same, just different sizes. They'd all be exactly the same shape, in other words. They'd all be similar shapes. So in this case, what is the eccentricity? What's the eccentricity in this case?
2√3/4.
Over 4, which would be √3/2, which is about 0.86. So you just wanted to measure it that way. Eccentricity is not anything that should ever be a challenge, because if you've told me where the foci are, you've already calculated the value of C. How do you know if you did it wrong? I did it wrong. How would I know that I did it wrong?
It's bigger than 1.
Yeah, that's a really, really simple test. Oh, if I choose the wrong number, I'm probably going to get something that's bigger than 1. Okay, and that would be, well, that'd be below average. You don't want to do that. All right. So, why do we study ellipses? I told you some information about parabolas last day. Why do we study ellipses? Do you see ellipses? We talk about parabolas, right? Sound waves, light, doing all these cool things. I have simple application. Do we have a lot of application for ellipses? Used to be people say, well, the elliptical trainers at the gym. How many of you used one of those? I don't. I tried one once. It made me feel like my hips were coming out of the socket. It was such an unnatural motion. But I remember when they first came out, this was the funniest thing I've ever heard. They said, it absolutely mimics the way all human beings walk. You all walk in an elliptical fashion. Do you realize how impossible that statement is? Because that means when I take a step, my foot would now have to dig into the ground. You realize the absurdity. Well, it's a half of an ellipse. No, it isn't, because none of you walks and then put your foot vertically down, because you would have a vertical tangent. Okay, then it's just this. No, there's no part of a human gait that in any way resembles any part of an ellipse. That's not even possible. It would be such an unnatural way to move. That was the selling point for years when they first came out. But the problem, the people were having a problem right away because it's so unnatural, the motion itself. I have an exercise bike. It goes in circles. A little easier to navigate that thing. Okay, no, that's not why we study ellipses. Where do we see ellipses?
Orbits?
Orbits. This is not something we proved from an equation. This is something we observed going all the way back to Copernicus in the 14th century. We observed that all orbits are elliptical. And that is a cool thing. Because you think common sense would say, you know, gravity is maintaining us from keeping us from flying away. Why aren't they circular? All orbits are elliptical. Another cool thing, like the moons of Jupiter, they don't all orbit in the same direction. They even go in different directions. It's crazy cool stuff. So is this useful to know that orbits are that's the sun. This is us. Okay. Our orbit is elliptical, but it is pretty darn close to a circle. Okay, the eccentricity is really close to zero. How do we know? What is one of the indications that we know that it's not circular? No. Yes, we are at a tilt. That is true. That has some effect also. But the fact seasons, the fact that the length of days changes all throughout the year and stuff. What day of the year, not the date, but the day in terms of a name, what day of the year is the Earth closest to the sun? Does anybody know? The first day of winter. What? Remember, the southern hemisphere, it's their summer. The furthest we are from the sun is our first day of summer. That feels backwards, but we're also in the northern hemisphere. That's the tilt part. But so why would this be relevant? Well, then we know where we are relative to the sun at any given time. Now, a long time ago, I wasn't there. A lot of people think I was. No, I wasn't there. You know, however many hundreds of years ago, we figured out how long it takes us to do one complete revolution around the sun. Anyone want to give me a rough estimate of that? About 365 days
And a quarter.
and about 6 hours. Is it exactly 6 hours?
Pretty close.
Pretty close. How close? Well, every 400 years we don't have a leap year. We were not supposed to have a leap year, by the way, 2000, because I had looked it up ahead of time, but we did anyway. I don't know who makes this decision, but because it's almost exactly 0.25, but it's not. So we're a tiny bit more, so we want to pull back once every 400 years. Why? Because then otherwise in a million years, summer and winter will change. But that extra, think about how many hundreds and hundreds of years if we hadn't done the leap year. We might now be, you know, in a completely different time of year, different month, different everything. So we know that. Now, why would that help us? Well, maybe we want to send somebody out into space and do stuff. Because there are other planets, aren't there? Oh, so if we know every other planet's orbit, do we know when we are certain, you know, distances? So here's us, and let's say, you know, Venus is right here. They're closer. Would this be a good time for us to fly to Venus? No. When would be a good time? Maybe when Venus is here? So it might seem kind of impractical to you because NASA, this is more important than it is probably to your daily life. But the fact is we know where every planet is going to be at any given moment. That we can figure out when is the opportune time to, you know, send something up. Okay? Does that make sense? Something that simple. But there's other really weird things that go on. And there's one that I've experienced in my lifetime. Most of you may not have. Okay, I learned this again. My kids were in school. I learned a lot of different things. For example, the difference between an asteroid and a meteor. This is all in the same context. Anybody know the difference between an asteroid and a meteor? They're actually the same thing.
Isn't it just once it enters the atmosphere?
Then it becomes a meteor. When it's out there, it's an asteroid. When it enters the atmosphere, it becomes a meteor. And we see this big ball of flame. Are they on fire? No, they're actually frozen. That was something I didn't know that until my kids were in school and I went to, you know, Reuben H. Fleet Space Theater, places like this. Went, really? They're frozen? I thought they were on fire. No, they're frozen. We're not seeing flames in that sense. It's a cool thing. So there's a particular asteroid. Mine is probably way over here. And it'll come cruising this way. Now, here's the thing. You guys, how many are in physics now? Okay, so you know this. Everything that has mass has a gravitational pull, right? everything that has mass. If you have no mass, you don't have any gravitational pull. So everything. So I'm on a run today, right? And let's say Natasha turns on the gravity extra strong today. What's that going to do? That's going to alter my path. Will it cause me to run into her? No, because I wasn't headed towards her. That's why we're not flying into the sun. We're never heading towards the sun. We're never going to fly into the sun. But you turn on the gravity, it alters my path. Okay? If you decided to turn off the gravity today, I could still run on the line. Right? So every one of you emits a certain amount of gravity. Now, gravity is determined by three things: my mass, your mass, and the distance. The greater the distance, it's an inverse square relation. So the greater the distance, the less the gravity. Double the distance, 1/4 the gravity, that kind of thing. But once something's in orbit, short of us getting hit by a large object and knocking us, that's not going to change. So something's headed this way, but it's not headed directly towards the sun. Otherwise it would fly into the sun. It's headed, and it's cruising along, and then it really gets a strong pull. In fact, so strong. Guys, how many have seen Armageddon? Love that movie. They actually have the physics more or less correct. If you remember, they went around the sun to come up from behind on the meteor, because you really don't want to fly towards the meteor that's going several thousand miles an hour. You understand that would not really be a good idea. Then quickly put on the brakes and so they flew up from behind. So this thing's doing this, and this particular thing was first noticed, I don't know, like 1,000 years ago. And it shows up every 86 years. And here's the craziest part. And it leaves, and it goes away. It goes completely out of our solar system, out of our view. And then like clockwork, it's going to come back. Now, it's a weird enough phenomena that our orbit is elliptical. And what is one of the foci? It's an ODA.
Distance from the sun.
Well, the sun is one of them. But there's no physical object that serves as the second focus. So why is this? I find this to be one of the great mysteries. By the way, I've never heard even an attempt to answer the question, because I think we gave up centuries ago. If there's no physical object serving as a second focus, then why isn't our orbit circular? Why is it elliptical? But it is, because we see this. We can clearly evidence that it's elliptical. But so none of the planets, right? All the planets have elliptical orbits around the sun. All of their moons have elliptical orbits around them. But there's no physical object emitting gravity. Isn't that an interesting thing? But I find this one more interesting. This thing's now left our solar system completely. It's really far away. And it's going to turn around and come back because it misses us. Okay? This one is called a comet. And I have fun with this because nobody mispronounced the name until the last time it came. And now you have half of the human race who can't read.
Halley's Comet.
Sorry, 2 L's. Is it?
C-O-M-E-T.
C-O-M-E-T. I was going to say commit. Well, I'll give you a hint. For 1,000 years, it was known as Halley's Comet until one person reading the news said Halley. And now all of a sudden, all humans think it's Halley. I have a niece named Haley. It's spelled completely differently, by the way. It's Halley's Comet. It's never not been Halley's Comet. And I laugh at this because it's really the same thing. I remember when Clarence Thomas, the Supreme Court Justice, was going through his, it was like an inquisition, when they were approving him. Oh my God, did they run that guy through the ringer. And he was accused of sexual harassment. And the newsreader read it as harassment. There is no word in the English language, harassment. There is no verb of you harassed somebody. It's harass, it's A-S-S at the end. Because one newsreader read it incorrectly. For the next few years, all of a sudden, I've been to really educated things where they talk about harassment. I'm like, that's not even a word. My God, how did you possibly come up with that? Because one person on the news, and by the way, what are the qualifications to be a newsreader? You just have to be,
Very fast.
Read it properly.
you just have to be pretty.
Oh.
You just have to be pretty. Guys you just have to be pretty. You don't have to have any intelligence whatsoever.
I feel like
So-
being able to read is important.
But that's the problem. I still remember in the early 2000s, Because I actually was on a jury, and the local sportscaster, I won't mention a name, very popular local sportscaster, had gotten selected for the jury. So they weren't doing the sports that week. They had the fill-in sportscaster. And I'm watching the news laughing. These were when the Lakers were winning championships. He kept referring to Shaquille O'Neal. Shaquille, he said it over and over again. Now, for those who don't know, Shaquille O'Neal, at that time was probably the most recognized athlete on planet Earth. And the newsreader kept saying Shaquille O'Neal. And I'm just dying laughing. So the next day when I'm going to court and I'm talking to the sports guy, I said, "Did you watch the news last night?" He goes, "Yeah, he got fired. he's not coming back." And this guy didn't get selected for the jury, so he ended up doing the sports the rest of the week. I still remember just dying laughing because, yes, being able to read is a really good quality, right? So we don't want to get our foci wrong as a result, because we'd never find Halley's Comet. And it would be, totally harassing you if I did it that way. It really bugs me, but I'm a math guy, but when people can't speak English, uncommon words, it's Halley's Comet. It will always be Halley's Comet. Yeah, it rhymes with Valley and Sally because it's essentially spelled the same. But anyway, it's a comet. We know exactly when it's coming back. The last time was in the 90s. I don't remember what year exactly. But it's one of these really crazy things. It's like, why is it turning around? I don't know, but it does. And we know when it's coming back. We can't see it, by the way. It'll be decades before we can see it. I just think that's just so cool. So we study ellipses, a lot of it, because of their astronomical uses. Okay? Hyperbolas. Those are tricky. Hyperbolas actually have practical application to us physically right now. So, hyperbola. I'm never going to ask you to draw a graph of any of these, but you need to know what the graph looks like and how to correctly draw a graph if you wanted to, so that it represents the thing you're looking at. Because when we do the three-dimensional versions of these, they can be really complicated. So hyperbola is the set of points on a plane where the difference in length to two fixed points is constant. Wait a minute, doesn't that sound almost exactly the same as the ellipse? Wait, I changed one word though. Difference rather than sum. Ooh, and actually that's kind of huge. That completely changes everything. So I can't do this one with a string. So I'll do it horizontally just because it's easier for me to draw it. I have a point, let's say it's right here. So whatever those two distances are, whatever the difference in those two distances are, is going to remain constant. So maybe I have another point here then, and I have maybe another point here, maybe another point here. I'm going to have points all over the place, and certainly I'm going to, whatever that difference is, I'm going to have points probably here. So it's probably going to look something like this. Oh, but wait a minute. Can't I have points on this side also? Ooh, so I'm going to have kind of a symmetric thing going on here. So at first, most people think it looks like two parabolas. Actually, it doesn't look anything like parabolas. I'm going to show you a little later how you can actually accurately draw a hyperbola by doing very little once you understand what's going into it. But so the hyperbola actually has two pieces, which is kind of interesting. So let's start the problem like we did with the ellipse by doing one that's centered at the origin. And we'll put the foci on the x-axis just to make it a little bit easier, okay? So here's one focus, here's another focus. Now it turns out the hyperbola is going to be, the focus is going to be inside the hyperbola. So it's going to look something like, like this, okay? I'll be more specific later. So let's pick a point. And again, we're going to call this C, 0. We're going to call this A, 0, and we will call that a vertex. So negative a comma 0 and negative c comma 0. These are the foci, these are the vertices, and unlike the ellipse, there's no other pair of numbers that I really need to worry about, okay? So let's pick a random point here. So now I have to figure out what is that constant difference. Well, let's start with one of the vertices. That makes it real easy. What is the distance from here to here? A plus c. What is the distance from here to here? C is bigger than A, so what is that distance? Would you agree it's C minus A? And what am I going to do with these values? Constant difference. Okay. So that would be A plus C minus C plus A. Wait a minute. I feel like I've seen this movie before. It's 2A again, isn't it? That's convenient. So that constant difference this time is exactly the distance between these 2 points. Oh, cool. By the way, if it opened vertically, that wouldn't change. That's still true. So all I need to do is solve this. Let's do what we did before. Let's throw one on the other side, square both sides. So d1 squared is going to be 2a plus d2 squared. I don't need this anymore. So that means this is going to be 4a squared plus 4a d2 plus d2 squared, and I'm probably going to get canceling all over the place. Okay. So let's calculate the d1 and d2 like we did before. What is d1? Sorry, that was x comma y. Let's put that in there. So what's d1? Probably looks, by the way, both d1 and d2 will be exactly the same as they were before, isn't it? Everybody agree?
Yeah.
So this is going to be, what? X plus c quantity squared plus y squared under the root. And d2 will be x minus c quantity squared plus y squared under the root. The difference is we're taking the difference between them, not the sum like we did before. So that's going to be the major difference. That when we squared before, that was a minus sign. But all the numbers that I'm putting in will look like the exact same numbers that we did before. So when we do this, d1 squared will be, and I will hold off squaring it first. And like before, we're probably going to get tons and tons of canceling. So let's go ahead and square this. And let's go ahead and square this one. Okay? So what cancels? Let's see. Well, I'm going to get the x squareds canceling. I'm going to get the y squareds canceling. I'm going to get the c squareds canceling. Agreed? Okay? Now, because this already has a positive coefficient, let's leave this here. Before we moved it in such a way to ensure positive coefficients, so let's leave this guy here. Let's send this one packing, and we'll send this one packing. Okay? So what will that give us? What is our new equation we will have? We'll have 4cx minus 4a squared equal to 4a times this stuff here. Agreed? And this, by the way, does this look very similar to what we had with the ellipse? Yeah, there's probably one sign difference, but everything else probably looks pretty much the same. So what was the first thing we did before?
Cancel fours.
Get rid of the fours, yeah. Now we're gonna square both sides, just like before. And when I do that, the left side will be c squared x squared minus 2a squared cx plus a to the fourth equals a squared. Now, let me go ahead and square the inside. Okay, x squared minus 2cx plus c squared plus y squared, because I gotta distribute that now. So a squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared. And like before, we would like all of our variables on the left side, all of our constants on the right, because then it's just easier to work with. Does anything cancel, first of all? So, I'm going to send that guy over, I'm going to send that guy over, I'm going to send that guy over. I always like to do that so I know where everything came from. All right, so my new left side is, I have a c squared x squared minus a squared x squared, so that's simply c squared minus a squared x squared. I have a minus a squared y squared. And in terms of the constants, I have a squared c squared minus a to the fourth, which is simply a squared times c squared minus a squared. That's what the right side looks like. Wow, this feels a lot like the ellipse, doesn't it? Does everybody see that? There's so many similarities. They're not the same. And this time, c is bigger than a, by the way. Last time c was smaller. So, like before, let's multiply through by 1 over. And if I do that, I'm going to get x squared over a squared minus y squared over c squared minus a squared, all equal to 1. All right. That's interesting. So, because that looks ugly, I'm just going to say, let's just call this b squared. If we know what c is and we know what a is, I have a difference of squares. Isn't there just a number there? You know, it could be 36 squared, 36 minus 16, whatever. There's a number there. Let's just call that number b squared, for lack of a better name. Notice this particular hyperbola opened horizontally. Can I have a hyperbola open vertically? Can I do this? Yes, and the way you would know the difference, it's actually really simple. It's not the size of a and b. It's the direction of the subtraction. Right now, if y were 0, x would be plus or minus a. Does that agree with our picture? But if x were 0, y would be imaginary. Didn't work. So whichever one is first in the subtraction, it determines the direction of opening, period. That's always going to be the case. When you have it in this form, equal to 1. I'm not worried about the shift yet. Don't worry about the shift. I'm going to call this roughly b squared. Now, I'm going to show you something that I do in Calc 1, and I've done versions of it in this class. I used to teach remedial algebra, and I would actually have the students draw the ellipses and hyperbolas, and I'd show them a really, really easy way to graph them very accurately, plotting points.